Here we go. And we're going to talk about Faraday's law, we're going to talk about motional EMF, we're going to talk about Lenz's law, and then a generalized form of Maxwell's equations. And we'll touch on Maxwell's equations. We're not going to dwell on them. A fair amount of this, well, it's a mixture. Some of this is conceptual that we need to sort out, and some of it is mathematical. So let's talk about Faraday's law to begin with. If I take a magnet, a bar magnet, and I hold it near a loop of wire, no battery connected, just a loop of wire, and I connect a sensitive ammeter to that loop of wire, sometimes called a galvanometer because it's really sensitive, nothing happens. The magnetic coil is inside a magnetic field, nothing's changing, no current flows. If I move the magnet towards the coil, then a current flows. If I hold the magnet inside the coil, no current flows. If I move the magnet away, a current flows. So with a little bit of playing around, I realized that the current is caused not by the magnetic field, but by the changing of the magnetic field. And that just seems like strange. We're used to, you know, if you have more cause, you get more effect. And stronger electrostatic fields cause more current to flow. I mean, you know, bigger voltages cause more currents to flow. And this is something that's changing. The bigger the change, the more current that flows. And so this is a quite remarkable observation. It's incredibly useful as well. So what we say is that there's, current flows when there's an electromotive force. So we say an EMF can be induced in the coil by changing magnetic field's position. I think of it, if I imagine just the loop, and I think of it as a bar magnet, I imagine the bar magnet having all these flux lines coming out of it. And as I push the magnet closer, I start off with only 2 flux lines going through it. And then as the magnet gets closer, there's more flux lines going through it. So whenever I increase the number of flux lines going through a coil, or decrease the number of flux lines going through a coil, the coil responds. The loop, in this case, the loop of wire responds. I think of it a bit like, imagine having a helix of wire. And imagine having some kind of like a feather duster, and you push the feather duster in, and it kind of causes the electrons to go whizzing around. That's not what's happening, but that's my visualization. It's not the position, it's the motion that counts. And I can see this. If I push, the current will flick one way. If I pull, the current will flick the other way. If I push with the opposite charge, with the opposite pole, then I get the opposite sense. So I can play with this thing. Well, I know enough about magnetism now to know that I can create a magnet using a current going round a coil. So I don't need this bar magnet. I just need a magnet. So let's make the magnet electrically. So I take a battery and I make a coil like a solenoid with a switch. Now, I'd like there to be as much communication between the magnetic field coming out of my magnet and the coil. I can put them end to end I can put them real close. But it turns out that the best thing I can do is actually put some iron type material inside my solenoid and have it travel round and go through my coil. It's almost like the magnetic field wants to stay inside that magnet, so all the flux lines which leave the magnet enter the coil. So it's a really efficient way of coupling things. And throughout, if you look at a transformer, if you pick up a power supply, they're often really heavy. And the reason why they're really heavy is because they're filled with transformers, and the transformers have these, they call them soft iron yokes. They're not a hard steel. It's a soft iron yoke. And it's really good at entraining magnetic field lines. It's really useful. So I can simply have my solenoid on one end, I put my sensor on the other, and every time I close that switch, I get a tremendous sudden increase in the magnetic field lines. It's like moving a bar magnet really fast towards my sensor. So I'll get a big deflection and a big deflection without any moving parts. That's also useful. So when I've played around with this, we get to Faraday's law. Faraday's law says that the EMF that is induced in a circuit is directly proportional to the time rate of change of the magnetic flux. That's d phi by dt. So we say my EMF, my induced EMF, this is my little epsilon, my little curly E. My induced EMF is equal to minus d phi b by dt. That's for one loop. If I put a whole bunch of loops in here, each one is affected the same way. So it multiplies. So if my EMF for a coil is minus n d phi b by dt. Now, I want you to notice, I'm all over here. My phi b is going through this guy, and my dt is how quickly that moves. It doesn't matter whether I'm using the bar magnet or this switch system on an electromagnet. It does not matter. What counts is how much flux is going through my receiving coil. And I'm inducing my EMF in this galvanometer circuit. So it's an EMF in something that has no batteries, that has no connection to mains. It's in a secondary circuit, which if you leave it alone is just a passive circuit. And again, this is incredibly useful because it means that I can transfer electrical energy through space. There's no wires. I can, if I'm willing to forego some efficiency, I can remove that iron yoke and simply have a coil connected to a battery with a switch, and simply have a coil connected to my meter. And that will work. And the energy is going from here into here. And I can put a pane of glass between there and have communication from one side of a pane of glass to another side of a pane of glass. And in fact, very many of us have this system. If we have a toothbrush, which is electric, we often have them where they just sit on a stand which is plugged in. The stand is plugged in. The toothbrush is not. And what you've got inside here is you've got that coil, which is the first part. And what you've got on the outside here is the receiving coil. So while ever this is stood on the nightstand, because of the changing AC, I got a changing magnetic field, which is inducing an EMF inside the receiver, which is charging up a battery. And so when I pick it up, it runs for a while. No wire connection. It's really, really excellent. This is, you can imagine how exciting this was for these people. Not because they could get a toothbrush out of it, that came a long time afterwards. But okay, so let's do something. We say, oh, I'm sorry, have I got no numbers in this? I can't, you got the clickers and we got no numbers. I'll ask you opinion questions. Coil of wire consists of 20 turns. The magnetic flux through the coil changes at a uniform rate. So let's just call that phi. Phi, I'm sorry. I was thinking about, I want to draw this in a different way, which will be more useful. There's my coil of wire. 20 turns. My flux. My flux goes from B initial, flux initial is equal to 8 Tesla meter squared. Flux final is equal to 12 Tesla meter squared. My delta T is equal to 4 seconds. So my flux is increasing in time. What's the EMF? EMF is equal to minus d phi by dt. That is, whose law is that? Is that Bonaquisti's law? It's good old Faraday. Good. That's Faraday. And if I want the full version, why not learn it with an N inside, so you never forget the fact that there could be an N. So my back EMF, my EMF, I'm sorry, is equal to 20. And let's before I do that, N delta phi by delta T. If it changes steadily, I can change my D's for deltas. This is minus 20, which equals minus N phi final minus phi initial over delta T. Making this hard work, aren't I? So that is going to be 12 minus 8 over 4, which equals minus 20 times 4 over 4. E is equal to minus 20. And what's the unit for EMF? Volts. Volts. Negative sign tells me the sense, the direction. And there's got to be some kind of way I can visualize that. We'll get to that later. Okay. So, very nice. Let's play with it. The key thing is a change of flux in time. And I made that change of flux in time in that last question by changing, well, I didn't say how I made the change in flux. I just said there was a change in flux. But, you know, I seem to recall, what was it? That my flux was equal to, what was the thing? B dotted with A, which equaled, that was the vectors, which equals the magnitude of B times the magnitude of A times the cosine of the angle. Yeah? So that tells me how I can change my flux. I can change my flux by messing with B. I can change my flux by messing with A. What area is this? It's the area of the receiving coil. I can change my flux by messing with the angle. What angle is this? It's the angle between the area vector and the field vector. So we've got to go back and recall that little bit about flux. We've got to remind ourselves. we say, well, if E is equal to, and again, I'm just getting more and more, I want to put that N in there. If E is equal to minus N d phi B by dt, and we remember that, well, yeah, Gauss's law equals the integral of B dot dA, and that was B times A times the cosine of theta, yeah? So then we say, well, okay, let's consider a loop of area A, which has an area vector, and magnetic field B, and I say, well, my EMF is equal to minus N d by dt of BA cosine theta. Yep. So an EMF can be caused by changing the B's magnitude in time, changing the loop's area in time, or changing the angle between B and A in time. A coil of wire consists of 40 turns. Magnetic flux changes from that to that in 14 seconds. What is its magnitude? And what I'm going to do is I'm going to put a clicker on, and I want you to do it. And while you're doing it, I'm going to do it. So I'll put some answers up in a minute once I've had time to think. Is it right? On yours? Oh well. I'm like 80% there, and then it drifts off and it comes back, and so that was probably just somebody walked into the room and talked to me, and it was like coil of wire. And N equals 40 turns. Let's see if it's right. And it changes at a uniform rate. So the flux. Oh, this is just a similar question. It's fine. I'll just do it. Flux. Flux initial equals 2 Tesla meters squared. Flux final equals 9 Tesla meters squared. My delta T equals 14 seconds. I turn around and say my EMF is equal to minus N d phi by dt. And I say that phi is equal to BA cosine the angle. Don't need that yet. So I say E is equal to minus N phi final minus phi initial over delta T. E is equal to minus 40. Final is going to be 9. Initial is going to be 2 over 14, which equals minus 47 over 14. So E is equal to minus 20 volts. Same answer. Wasn't the same question, was it? Hope not. Probably was. 10 turns. Strength of the magnetic field that passes through the coil is 12 newtons. Is this one done? No. Do it. Okay. Do it, do it, do it. So draw yourself a quick diagram and note down what the number of turns is. And then what are you given? You're given a magnetic field in this case. Oh, this is an area. Okay. So that's 12 Tesla. And then it gets bigger. So A initial is equal to 3 meters squared, and A final equals 7 meters squared, and the time is delta T equals 5. So I'm going to say So let's just have a quick look at this. So first of all, my diagram, I'm drawing my loop, and I have my magnetic field goes through it, and then I have an area change this time. So the things I look for, is it flux that's changing? Is it area that's changing? Is it angle that's changing? What's changing? Something's got to change in time. And in this case, it's area. It could be B, I'm sorry. Is it flux, which is the overall thing? Or is it the B, the A, or the angle that's changing? And in this case, it's the area that's changing. So, okay, I know the number of turns. I know the magnetic field strength. I know that's constant in this case. But my area is changing. And so I have my initial area, my final area, and I know my time. And so I state Faraday's law, EMF is equal to minus n d phi by dt. And if it changes smoothly, I can say it's minus n delta phi by delta t. And I remind myself that my flux is equal to B times A times the cosine of theta. And actually, what's bad about this question is that this works on the principle that my magnetic field is at 90 degrees to my area. I want my area vector and my magnetic field to be parallel for this to work, because I'm assuming a value of 1 here. And I didn't actually state that in this write-up, which is a poor write-up. So then I say, well, EMF is equal to minus n B dA by dt, because cos theta equals 1. And then I'm kind of saying, well, it's A final minus A initial over delta t. And I go minus 10, 12, 7 minus 3 over 5. And the rest is just numbers. Yeah. So I know it's to do with the changing flux, and I know my flux could be caused by a change in B, a change in A, or a change in angle. And this time I changed my angle. I changed my area. How did it do that? I don't care how it did that. It did it, you know. In a magnetic field going through the room, we made the coil wider. We made it bigger. That's all that matters. Coil of wire consists of 15 turns. The strength of the magnetic field that passes through the coil is 12 Tesla. The coil has an area of 3 meters. The angle between the magnetic field vector and the coil area vector changes from 25 to 70 in 4 seconds. What is the magnitude of my EMF induced? So I'm actually going to draw I'm going to draw it a bit more carefully. So I'm looking from the side, and here's my B, and I have my area vector at A. And I know my N is equal to 15 turns. And I know my B is equal to 12 Tesla. And I know my A is equal to 3 square meters. Or 3 square meters. I know the angle between the magnetic field vector and the coil area vector goes from, so this is my theta, and theta initial equals 25 degrees, and theta final is equal to 70 degrees. Because it says the angle between the magnetic field vector, that's my B, and my coil area vector, remember that's a coil at 90 degrees to the area of the coil, is equal to 25 and the time, that takes 4 seconds. So there's all my information. So I say, well, Faraday's law says that EMF is equal to minus n d phi by dt. And if you like, I can say my phi is equal to BA cosine theta. So I can say my EMF is equal to minus n delta phi by delta t, which equals minus n, let's say B's constant, A is constant, delta cosine theta over delta t. So E is equal to minus n B A. And this is, I've got to be careful here. It's going to be cos theta final minus cos theta initial over delta t. Now I can do it. E is equal to minus n is 15. B is 12. A is 3. Cosine of 70 minus cosine of 25 over 4. So EMF is equal to minus 15 times 12 times 3. And now I need to get my calculator. Hopefully I brought my calculator today. I usually do. Here we go. And the first thing I'm going to check is that I'm on degrees, because I spend a lot of time on radians. So I look at my calculator and I can see it's in radians. So I press DRG and click over to degrees and then say enter. So now I can see from the display I'm in degrees. And then I do cosine 70, enter. And that's going to be 0.342 minus, clear, cosine 25, enter, and that's going to be 0.906 over 4. And now I can just do calculator all the way. So I'm going to go 15 times 12, enter, times 3, enter, times bracket. I'm going to do 0.342 minus 0.906, close bracket, enter. And then I'm going to divide it by 4, divided by 4, enter. So that should be minus 76.14 volts. Yep. Agreed? Yeah. Yes, so thank you. Save my bacon. Yeah, positive. Forgot my minus in front. And what do you think, apart from missing the sign, what do you think the most common mistake is that I'll see on a test? Yep. Pardon? Yeah, exactly. What people will do is they'll go, oh, well, I can just do 70 minus 25 is going to be, what, 45? And they'll go cosine 45, and that's not the same as cosine 70 minus cosine 25. That's the most common mistake. Yeah. So you got to be just set an alarm for that. Just be, you did it in what, trig, and you hadn't done it in probably 2 years or something. And it's just like it's not in the forefront of your mind. So set an alarm for that. Be careful about that. Okay. So we introduced Faraday's law, and we've done 3 typical questions. Let's talk about a thing called motional EMF, not emotional EMF, but motional EMF. And this is how we play with this thing. Now, a good example of this would be if you take an aeroplane with wings, and it's a conductor, it's made out of aluminum, probably, and it flies inside a magnetic field because the Earth's got a magnetic field. So those electrons and the positives charges, and they're moving inside a magnetic field. So there's going to be a small force on them. We did this before. F equals QV cross B, remember. And the interesting thing is that because of the opposite charges, the forces are in opposite directions. So you could get all the positives being pushed to one end of the wingtip, to your left-hand wingtip, and all your negatives being pushed to your right-hand wingtip. And that's an EMF. That's a battery. Now, it's not going to go like that forever. You're not going to get billions of volts, because those positives don't want to be next to each other, and they want to be with the negatives, and the negatives don't want to be next to each other, they want to be with the positives. So we have a balance between our magnetic force and our electrostatic force. And that's the game we're going to play here. Okay? Now I'm going to make it a bit more easy. I'm going to have a vertical magnetic field, a horizontal plane, you know, all that kind of stuff. I'm not going to worry about the realistic view of it, but we'll go. So we say consider a metal rod or a plane that travels through a uniform magnetic field. The motion causes charge separation. Positives go to one end, negative goes to the other. So charge builds up at the ends of the metal rod. This creates a potential difference between the ends of the metal rod. At equilibrium, the electric force is balanced by the magnetic force. And we know from before that Fe is equal to QE. And we know that FB is equal to QV crossed with B. So these two guys are equal to each other. So we get the electric field is equal to V cross B. And if we remember that delta V is equal to, well, do I remember that? It's, let's have a look. My electric field is my force per coulomb, and my voltage is my joules per coulomb. And how can I go from force per coulomb to joules per coulomb? Oh yeah, I multiply by a distance, because force times distance is work done, which is joules. So that makes sense. Even if I don't remember it, I could finagle it out. So my potential difference is equal to E times delta L. So my potential difference is equal to E times delta L, which equals to V cross B delta L. And for orthogonal system, where these guys are all nicely at 90 degrees to each other, my V is at 90 degrees to my L, and my B is at 90 degrees to both of them, that simplifies to BLV. So my EMF that's created between these two lengths is BLV, the magnetic field strength times the length of my rod times the velocity with which I move my rod. Three-meter length of rod moves in a uniform 20 Tesla magnetic field at 8 meters per second. The rod's length is parallel to the x-axis. The magnetic field is parallel to the y-axis. The rod's velocity is parallel to the z-axis. What EMF is induced? The quick way is you go, well, EMF is equal to BLV, little v, so let's put a little curly end on it so I'm not confusing that with voltage. And so for this there would be 20 times my length, which is 3, times my V, which is 8, which is 3 8s are 24, 240, 480 volts. But if I couldn't remember that, remember that it is about the balance between your electric field and your magnetic field. Electric force and your magnetic force. So I go Fe is equal to E times E. And I go FB is equal to QV crossed with B. And I put these two guys equal to each other. So my E is equal to, sorry, this is a Q as well, isn't it? Because it's just the same charge. Two symbols for the same thing. So E is equal to V crossed B, which equals, E is equal to V times B times the cosine of the angle between them. Yeah? And then I go, well, hold on. My delta V is equal to E times L. So therefore, delta V is equal to L times V times B times the cosine of the angle between. But that goes to 1 because it's orthogonal. So delta V is equal to BLV. So if you can't remember that equation, you can get to it. Yeah? Yes? I can't hear what you're saying. Oh, sine. I'm sorry. Yeah, thank you. I need spring break so much. I am so tired. Okay. So either way, you can get to it, yeah? By the way, about 20 years ago, so how do they power the space shuttle?
Is it solar?
Once they're in space, I meant once they're in space, yeah. Once they're in space, what they tend to do is they pull out solar panels, and you know they'll run it using solar panels, or an awful lot of your long duration satellites will use solar panels. But somebody had this great idea. They said, you know, if we take a satellite, it's going around the Earth all the time. So I've got a V, and it's in a magnetic field, which for the large part is quite steep. So I have a B. And the only thing I'm lacking is an L. So they said, maybe I can, the L only has to be a long piece of wire. So they did this experiment on the space shuttle where they had this like 5-mile coil of wire in the back of the space shuttle. And they just started it, paying it out. Now, it's kind of difficult when you think about it because there's no wind resistance. So how does it know which direction to go in? It turns out there is a little bit, there's a lot of particles of dust there, so although it's a very skimpy wind, there is a little bit of a skimpy wind. And so they started paying it out, and as the L gets longer for a given B and a given V, you know, if the L gets longer, you get more voltage, which means that you can power up your satellite. You don't necessarily need solar panels. I can see a problem with this already because up there at the moment, there's probably, I don't know how many, probably thousands of satellites at different levels, but it gets quite crowded in near-Earth orbit. So can you imagine a 5-mile piece of wire connecting with a 5-mile piece of wire? It would be an issue. So it was more a principle experiment than a real situation. But what they found was that although there's not much dust, there's no atmosphere, but there's not much dust where the shuttle tends to fly, there is some. And what happens if you have a little flag and you have it by the side, like those little game flags like they have for the Buccaneers and all that, people put them in their windows. As they drive faster and faster, what happens to those flags? They flap, don't they? And that's what this started to happen. It started to flap backwards and forwards. They hadn't got to 5 miles, and they started getting this, and it started causing this thing to yaw. And they said, end of experiment. But they were going to try it. They started the experiment to try it. So, okay. So that was, all right, so that's motional EMF. It's basically saying, you know, okay, it's motional EMF. Let's talk a little bit about an application of this. And I must confess, I think they go around in circles here, so I'm gonna go through it the way it's in the book, but then I'm gonna kind of talk a little bit about. I want to give you a little caveat here. So here we have our rod, like we had before, moving in a magnetic field. And rather than the rod just moving and developing an EMF, why don't we have the rod run on rails? So we have these 2 rails that are fixed, and we have a piece of wire connecting the rails with a resistor in it. So we have a loop, don't we? It's a crude loop, but we have a loop. There's a conductivity path which goes in a square. That's a loop. So I can interpret this in terms of EMF, motional EMF, and say what will happen. Or I can interpret this in terms of Faraday's law and see what happens. Because they're both 2 ways of talking about the same thing. Does that make sense? I can just take this blue rod into account, moving through this magnetic field, and say, what's the EMF, and how does that EMF drive a current through this resistor? Or I can turn around and say, oh, I have a changing area on a loop, and because of Faraday's law, that creates an EMF, and how does that EMF drive a current through the resistor? So there's two ways to get to the EMF. There's the motional EMF way, and there's the Faraday's way. And this is kind of telling you it's the same thing. So we say, consider a circuit that is moving, that has a moving section. That is the sliding rod. The area magnet field enclosed by the loop can be changed. The induced EMF acts like a cell. So let's look at it from the Faraday point of view. From the Faraday point of view, I say, well, my flux is equal to, well, let's have a look. It's the magnetic field times the area. I missed a line out, didn't I? Flux B is equal to, I should have said, B dot A, which gives me B times the length L, which is that guy, times X, which is down there. That's just area. That's area. I'm sorry. That's area. And the B's the B, yeah. Okay, so using Faraday's law, my EMF equals minus d phi B by dt, which equals minus d by dt of BLX, because my phi B is BLX. And so my EMF is equal to minus, take out all the constants. B's constant, L's constant. Oh, it's the x by dt. And the x by dt is my velocity. Isn't that what I just got? Didn't I just derive that using motional EMF? So it's the same thing, isn't it? It gets you to the same point of view. So then we say, okay, for the circuit with resistance Ri is equal to E over R, EMF over R, which equals BLV over R. Cool. And I can think of this, so this is the circuit of the reality, and this is the equivalent circuit, and I basically have an EMF induced. There is no battery in this system. The EMF is induced by this motion. Okay, how are we doing? We've got 15 minutes. So this is great. Move a rod inside a magnetic field and you get a voltage. There is a problem, and that is you get an energy. Once you get your rod to the velocity, it takes no energy to keep it at that velocity, and yet you have a continuing stream of energy for the rest of eternity. And that's not going to happen. So there's got to be something that's fighting you, and there is. And it's called Lenz's law. Lenz's law says, oh yeah, you're going to have to work to keep this motion. It's not a freebie. You're going to have to do work. And, you know, the work will be even more than you're going to get out of it, because, you know, you never get breaking even. So let's talk about that. So Lenz's law says that the polarity of the EMF is such that it tends to produce a current that creates a magnetic flux to oppose the change in the magnetic flux through the area enclosed by the current loop. Basically, think of Lenz's law as saying, whatever you do, I'm going to try and stop you. I'm just going to try and keep the status quo. And it has to do that, because otherwise you're getting a freebie. So that we know there's going to be something like this. So here's my rod, and here's my magnetic system. We say the current flow in the loop that we have just created by this motion sets up a magnetic field that offsets the change in the flux that caused the thing to start with. So let's think about it. Faraday's law says my EMF is equal to minus d phi by dt. It's the flux that matters. And I'm getting it. Think of the flux as being the number of arrows. So there's 1 arrow, there's 2, there's 3, there's 6, there's 9, there's 12 arrows. Okay? So my flux is 12 to begin with. And then because I move this thing to the side, I now have 20. Okay? My flux increased. What Lenz's law says is the very current that you just created will cause a magnetic field. Flowing current causes a magnetic field, which will create flux lines which will be in the opposite direction to what you just had. So we'll get, oh, I'm sorry, but I'm cancelling you out. Now, we've got a fair bit of signs to worry about here. Let's see if we can figure it out. F equals Q V cross B. So if you point your fingers along the red V line and you curl towards the magnetic field, then we know that our positives go to this top end. Agreed? Our negatives go to the bottom end. And current wants to flow from positive to negative, so that's confirmed my current's direction. So that current direction is right. Agreed? Yeah? That current is flowing like that. And if I imagine this little bit of it, and remember your right-hand corkscrew rule, I'm going to draw it over here. Here's the current flowing, and you have this circular current loops. So I'm sorry, circular magnetic field loops, and it goes with like a corkscrew. You point your thumb in the direction of the current, and the magnetic field points in the direction of this, like that, like a corkscrew. So if I, on this back edge here, have a current flowing like that, then that means that my magnetic field is going into the page on that side, because that's here, and out of the page on this side, because that's there. And that's where this thing with a dot in the middle comes from. So the original magnetic field was going into the page, and the induced magnetic field is coming out of the page. Yep. So does that make sense? Have I justified this equal, and well, not equal, but this oppositeness? The fact that the current flow in the loop creates a magnetic field that offsets the change in flux caused by the larger loop area. It does the opposite. And if I reduce the magnetic flux, then I just got rid of these guys. So now let's see. So now my V's in that direction. So I point in terms of V and I curl my finger so that I show that the positive charges go to that end and the negative charges go to that end. So this current is in that direction, which means here it's in that direction. There's my I. And then using this thing, if I do the right hand rule, the corkscrew rule, they are going into the board. So what happened is I lost these guys. I'm sorry, I'm drawing this. This should be over here. I lost these 8. And while I was losing these 8 because the current's flowing up there, I was creating more of them. Again, I'm trying to maintain status quo. So that is good old Lenz's law. And I'm going to stop there for a minute because I'm near the end of this thing.